Hello, everybody. Welcome to my first ever public live stream. I can't begin to tell you guys how excited I am about this. I just want to apologize in advance. This is my first time ever doing this. If anything is bad quality or if there's any kinks that we need to work out, please use the chat and just let me know what's happening. And I think this is going to be really good. I'm super excited about it. Please just use the chat as much as possible. Interact with each other. And also, I would love to know where all you guys are coming from. So if in the chat, if you could just let me know where you're from, and I would love to find that out and just get to know you guys a little bit better. So for this particular live chat. Or for this particular live stream, we're going to be talking calculus. Thank you from Unknown Don, India. Thank you for joining us. Thank you from Amman, India. Also, thank you for joining us. This is awesome. Lots of people from India. Nahid from Canada. I'm glad you can join us as well. Samia from the United Arab Emirates. Thanks for joining us. Oki from Slovenia. Oh wow, we got people from all over the world. So this is exciting. And I just want to encourage everyone to use the chat as much as possible. Thank you so much for joining us. We are going to be talking calculus. So what I'm going to do is I'm going to work out a bunch of problems. And during the problem, I'm not going to be able to focus so much on the chat. So I want you guys to help each other out. And then after the problem is done, then I will be able to answer your questions, look at the chat, and hopefully I can help you guys out as much as possible. So I did receive a lot of questions on integration. So I created a lesson that's going to go over a little bit about integration, a little bit about finding the area underneath a curve. I hope you guys learn a lot from this, and I'm excited to do it. So once again, thank you much for joining. CB Mafia from Jamaica, glad you can join us. Yusuf from Sweden, glad you can join us. And let's get started right away. So here in this problem, we need to evaluate the indefinite integral of the square root of x minus 2 over x cubed plus x minus 5 times dx. And this is as basic as it's going to get, just because we have a bunch of x terms by themselves, and the only thing we need to do is integrate these x terms. And we do have like a 2, and we do have an x that's in the denominator of this, but we still just have a bunch of x terms that are isolated by themselves. Because of this, this is a basic integration problem, and and I wanted to start with the basic problem just so you guys have a good understanding when we get into some more advanced problems later on. So let's just get started right away with this example. And the first thing I like to do is get rid of any square roots. And the first thing I like to do is get rid of this x cubed in the denominator, and I'm going to rewrite that in the numerator. So let's rewrite this square root as a 1/2 exponent instead, because a 1/2 exponent is exactly the same as a square root. And if you remember from algebra, a positive exponent in the denominator can be rewritten with a negative exponent in the numerator. So x cubed in the denominator could be x to the negative 3 in the numerator. So I'm going to put an x with a negative 3 in the numerator, and the rest of the integral is going to stay exactly the same. And the basic idea behind integration is you want to add 1 to the exponent. With a derivative, you would subtract 1 from the exponent, but with an integral, you add 1 to the exponent. That's why it's called the anti-derivative as well. So we want to add 1 to all of these exponents after we integrate. So let's start with our 1/2 exponent. If we add 1/2, or if we add 1 to 1/2, we have 3 over 2. And with integration, you always need to divide by the same. So since we have a 3 over 2 here, then we need to divide by 3 over 2 as well. All right, and we're moving on to our next term, our negative 2x to the negative 3. Negative 3, if we add 1 to this exponent, negative 3 plus 1 is a negative 2 exponent. So instead of a negative 3 exponent, we'll have a negative 2 exponent. And once again, we got to divide by the same. So since we have a negative 2 exponent, we're also going to divide by a negative 2. And moving on to our next term, we have a positive x. And you can imagine that there's a 1 exponent on top of this x. So if we add 1 to 1, we have an exponent of 2. And once again, we got to divide by the same. So we'll divide by 2 as well. And then moving on to our constant of negative 5. Anytime you integrate a constant, you just add an x. So that negative 5 after we integrate will be negative 5x. And with indefinite integrals, one thing we have to remember is that we always have to add a constant plus c. This represents, can be any constant as well. So now we have completely integrated this problem. The only thing that we have left to do is to simplify this as much as possible. So let's simplify this using a bunch of algebra. And that's the hardest part probably about calculus, is all the algebra that's involved. So I really highly recommend to brush up on your algebra skills if you're struggling with all of the simplifying with all these calculus problems. But so let's get started with this 3 over 2 fraction that's in the denominator. You can never have a fraction within a fraction. So to get rid of that, we are going to multiply by the reciprocal. Dividing by a fraction is the same thing as multiplying by the reciprocal. The reciprocal of 3 over 2 is 2 over 3. So we're going to multiply by 2 over 3 instead of dividing by 3 over 2. And the rest stays the same. So we still have our x with a 3 over 2 exponent. And if you notice in our next term, we have a negative 2 and in the numerator and a negative 2 in the denominator that cancel each other out. So the only thing we're left with is a positive x with a negative 2 exponent. So we have a positive x with a negative 2 exponent. And if we moving on, I like to stay consistent since we have a multiplying fraction over here. I'm going to rewrite this next term the same. So instead of dividing by 2, I'm going to multiply by 1/2. And that doesn't really matter, but I just like to stay consistent. So we have a 1/2 x squared term. Our negative 5x stays the same. And we have a constant of plus c at the end that we can't forget. All right, so now we have simplified this a little further, but what we have to do, what we still have to do is get rid of this negative exponent, because we can never have a negative exponent in our final answer. Just like before, we have to rewrite this with a positive exponent by flipping it into the denominator. Once again, a negative exponent in the numerator is the same thing as a positive exponent in the denominator. So we're going to have a positive x squared in the denominator, and we'll have a 1 that's in the numerator. And the rest of the problem stays exactly the same. We have 2/3 x with a 3 over 2 exponent, and we have a positive 1/2 x squared and a minus 5x plus c. And I think we have simplified this as much as possible. So this is our final answer. This is our solution to the problem. We have officially integrated that integral. And that was a very, very basic integral. The only thing we had to do is just add 1 to each exponent and then divide by the same. And I'm going to get into a little bit more advanced problems a little later on in this live stream. So stay tuned for that. But This is the basic idea, and I wanted to go over a basic example before we go on any further. So does anyone have any questions? How are you guys enjoying this? Oki124 says this is very interesting. I'm glad. Yeah, I'm glad you find it interesting. Glad we could help out. Aman Puni says he said my name. I'm glad you can join us, Aman. Thank you for subscribing, CB Mafia. Thank you for that. Marge Ken says he's enjoying the math. I'm glad you're enjoying this, Marge. All right, so it doesn't seem like you guys have any more questions for this problem, so let's move on a little bit further. So that was an indefinite integral. And for this next example, we are going to go over a definite integral. And the cool thing about definite integrals is that they can be used to find the area underneath a curve. So here for this example, we want to find the area under the curve f of x between x equals 0 and between x equals 2. So we have this curve in red, which is f of x, which is equal to x squared. So we want to find the area underneath x squared between 0 and 2. And I labeled this area that we're trying to find in green. So this area in green is what we are trying to find. And the cool thing about definite integrals is that we can find the exact area underneath this curve in green. We can find the exact area using definite integrals. So it's pretty cool. And just to give you an idea of how this works, we can use rectangles to approximate the area first. So let me show you how we approximate this area. And then using this approximation, it'll give you an idea of how we get an exact area using definite integrals. So let's say that we just use 2 rectangles to approximate this area. So if we use 2 rectangles, they're each going to have a width of 1. And let's just say the right side of each rectangle will touch the top of the curve, that will touch x squared. So this right side is going to touch the top. And it doesn't matter if the right side touches the curve or the left side, you just got to make sure that you stay consistent. All right, and I'll draw this next rectangle to the left. Once again, it's going to have a width of 1 unit. And the right side is going to touch the top of the curve. And then I'll finish off this rectangle over here. And if we take the areas of these rectangles, it'll give us an approximation of the area underneath the curve. But here is the problem with this approximation. Look at all of this area in these rectangles that is not part of the curve. Look at this area that I'm coloring in blue. This is not part of the area that we're trying to find, so our approximation, if we add these 2 rectangles together, is going to be a pretty big over approximation, and it's not going to be that accurate. In order to make a better approximation, what we can do is use even more rectangles. And I drew a picture for you already just to save a little bit of time. Look what happens if we use a lot more rectangles. Look at all this area in blue. Look how much less it is using all of these rectangles compared to the picture when we only used 2 rectangles. Look how good this approximation is. It's still not going to be exact, but it's going to be a very, very good approximation of the area in green. So using this same idea, imagine if we use an infinite amount of rectangles. If they were just so tiny that we use an infinite amount of rectangles, that means that our approximation wouldn't be an approximate anymore. It would be an exact value. We would get the exact area underneath the curve. And that's why a definite integral is so fascinating, is because it uses these infinitely small rectangles and then we can find an exact approximation. So I think that's pretty cool. And that's the idea behind using definite integrals. So In order to find this area in green, what we can do is set up this definite integral. And what we're going to do is use the same symbol as an indefinite integral. And at the bottom of a definite integral, you put your lower bound. And our lower bound is 0 since we're starting at 0. And our upper bound is going to be 2 since we're going from 0 to 2. So we'll put a 2 on top of the integral. And then what we're going to do to find the area is put our curve of x squared inside our integral. And we are going to multiply this by dx. And just to give you an idea of what this represents, this x squared kind of, I guess you can say it represents the height of every rectangle. Just imagine an infinite amount of rectangles, and this x squared is the height because each rectangle, the top of it is touching the curve. So the height is going to be equal to whatever the curve is at that point. So our x squared represents the height, and this dx term represents the width of every rectangle. And so what we're doing with this definite integral is that we're adding all of these rectangles together from 0 to 2, these infinite amount of rectangles from 0 to 2, and we're going to get an exact area, which I think is pretty fascinating. And if we just get started right away, this is almost exactly identical as an indefinite integral. The same idea is that we want to add 1 to our exponent and divide by the same. So I'm going to add an exponent, or add 1 to our exponent of 2. So now we'll have an exponent of 3. And once again, we got to divide by the same. And on the right side of our bracket, we're going to put our upper bound of 2 and our lower bound of 0 on the right side of the bracket. So at this point, it's identical to an indefinite integral. And here's where it changes just slightly for a definite integral. So what we're going to do, or what I like to do, is to put 2 separate brackets, and they are going to be subtracted with each other. And inside each bracket, it's going to be identical, almost identical to x cubed over 3, but instead of putting the value of x, I'm going to leave it blank. So I'll put a blank parentheses with a 3 exponent on top of it. And I'm going to do the same thing for this bracket over here. I'm just going to put a 3 in the bottom, and wherever there's an x, I'm going to leave it blank. And then I can't forget about our exponent of 3 on top. And in our first bracket, I'm going to put our upper bound of 2 everywhere there was supposed to be an x. And in our second bracket, I'm going to put our lower bound of 0 where there was supposed to be an x. And at this point, it is just simple arithmetic. So we have 2 cubed, which is equal to 8. 8 over 3 is our first bracket. And then in our second bracket, we have 0 cubed, which is just 0. 0 over 3 is also equal to 0. So we have 8 over 3 minus 0, which just simplifies to 8 over 3. This is our final answer to our definite integral. So what does this tell us? This is pretty cool how we can find this area in green underneath the curve is equal to 8 over 3. That is the exact area under the curve. And a definite integral, it doesn't matter what shape the curve is, we can find the exact area underneath any curve. So I think that's pretty fascinating, and I think it's pretty cool. I hope you guys could follow this. And do you guys have any questions about this problem? How are you guys enjoying this? How are you guys enjoying this live stream so far? Aman's trying to help. He says there are infinitely many rectangles, but we can take one single rectangle, a strip, and integrate it from a lower upper limit. Yes, you can approximate. The idea is that you can approximate using a finite amount of, if you use 2 rectangles or if you use 100 rectangles, you can get an approximation, that's not an exact value. But the idea with integration is that we use an infinite amount of rectangles, and we can get an exact value of the area underneath the curve. So I hope you guys could follow this pretty easily, and it seems like you guys are enjoying it, which is pretty awesome. And I'm having a great time doing this. So thanks for coming, guys. You guys want to do one more problem? How does that sound? All right. Before we were doing a lot of basic examples, and for this problem, I'm going to go over a little bit more advanced example where we have to use U substitution. So once again, this is a little bit more advanced, and I want to just thank you guys for coming before I get started in this problem. Once again, I want to encourage you guys to use the chat as much as possible because I'm not able to pay attention to the chat while I'm working on the problem. So if you're having any questions, I'm trying to help each other out. And also too, I want to just apologize for any person who wanted me to work out a problem that I couldn't work out, just because there's only so much we can do in one lesson. But I just want to let you know that I do offer homework solutions for any of you guys that need extra help. Just send me an email to homeworksolutions@mathmeeting.com, and I can help you out with that. So, but let's get started right away with this example where we need to use U substitution. All right. So notice that this is not a basic example like it was like earlier, because we don't have a bunch of isolated x terms. We have this parentheses followed by an exponent of 3, and that's all being multiplied by an 8x. So obviously we can't use the same technique as in the earlier example, and I'll go back to that right now. This earlier example before, notice how we had a bunch of isolated x terms and a constant of -5. Because of that, we could use a basic integration technique and just add 1 to the exponent. But for this example, we have this parentheses followed by the exponent of 3 being multiplied by an 8x. So we need to use some other technique to evaluate this integral. And this technique that we're going to use is called U substitution. So let's just get started right away with this example. And the first step in U substitution is to pick U. All right. So step number 1 is to pick your U. And this will make a lot more sense after I do it. And the basic idea for picking your U is that when you take the derivative of that, it's going to be equal to the rest of the integral. And this will make a lot more sense once we get started. Most of the time, for an example like this, your U is always going to be the inside of the parentheses. All right? So this inside of the parentheses, and I'll change colors here. This inside of the parentheses, x squared minus 5, we're going to let this be our U. So U is going to be equal to x squared minus 5. And the idea behind picking our U is that when we take the derivative of this, we want it to be equal to the rest of the integral, which is 8x dx. So this will make a lot more sense once I take the derivative. So what's the derivative of U? If we take the derivative of U, it's going to be equal to the derivative of x squared, which is just equal to 2x, plus the derivative of -5, which is just equal to 0. So we don't have to write that. And we can't forget that we're taking derivative with respect to x. So we'll put a dx at the end. All right. So notice that we have an 8x dx in our integral, and we have a 2x dx as our du. So it's almost the same. All we have to do is just multiply it by 4. We want to make this over here exactly the same as the integral. So we have a 2x dx, and we want to make it exactly 8x dx. Okay, so how do we do that? We can do that by multiplying both sides by 4. If we multiply du by 4, and we multiply the right side of this by 4, 2x times 4 is equal to 8x. And now notice how our 8x dx is exactly equal to the rest of our integral, which is exactly what we want. Okay, so now at this point, we're ready to perform our u substitution. All right, so let's just get started right away. So what I'm going to do is, instead of writing x squared minus 5, and let me change colors right here. So we have an x squared minus 5. We know x squared minus 5 is equal to u. So instead of x squared minus 5 cubed, I'm just going to put u cubed. So that's equal to u cubed. All right. And we know that 8x dx is equal to 4 du. So instead of putting 8x dx into our integral, I'm going to substitute and put 4 du instead. Once again, 8x dx is equal to 4 du. All right, and just to make this a little bit more simple, I'm going to take this constant of 4 and I'm going to multiply it in front of the integral. You can always take constants and multiply it in the front whenever you integrate, so that doesn't change anything. So I'm going to take that constant of 4, bring it to the front of the integral, and the rest of it stays exactly the same. We have u cubed. We don't really need to put the parentheses there. And then we still have our du on the right side. All right, so now we have a really basic integral. We just have, before we had a bunch of, in our first problem, we had a bunch of isolated x terms, and which all we had to do is add 1 to the exponent. And the same idea here, we just have one isolated u term, and all we have to do is just add 1 to the exponent and divide by the same. So let's do this. So I'm going to add 1. We had an exponent of 3, so I'm going to add 1 to the exponent. So we have u with a 4 exponent now. Once again, we got to divide by the same. And we can't forget that we are multiplying. We still have our 4 in front of the integral that's being multiplied. And also, this is an indefinite integral, so we can't forget that we have to add our constant of plus c. All right, so now let's just simplify this as much as possible. Notice how the 4's cancel each other out, and the only thing that we're left with is u to the 4th. So this is equal to u to the 4th plus c. And at this point, we can't simplify it anymore, but we can't leave our answer in terms of u because we started in terms of x. So our final answer also needs to be in terms of x as well. And we know that u is equal to x squared minus 5. So we can plug x squared minus 5 anywhere that there is a u. So let's go back down, since we know that u is equal to x squared minus 5. And I'm just going to plug in an x squared minus 5 everywhere there's a u. And we can't forget that there's a 4 exponent on top of it. And we can't forget about our plus c as well. So this is the final answer to our problem. We have, this is equal to x squared minus 5 to the 4th power plus c. We have officially used our u substitution method to evaluate this integral of 8x multiplied times x squared minus 5 cubed. So I'm hoping that you guys could follow that quite easily. It's a little bit more advanced than a basic integration technique, but once you do a bunch of problems and you get the hang of it, it's actually not that bad. So I hope you guys enjoyed it and could follow it as easily as possible. So this is the last problem that we're going to go over today. I'm glad that I could help you guys out with some integration techniques. Once again, I apologize if you guys had any problems that I couldn't go over, but I do offer homework solutions to anyone who needs any extra help. Just send pictures of any problem you need help with to homeworksolutions@mathmeeting.com, and I'll get back to you, letting you know how long it will take and stuff like that. So this is what you can do if you need any extra help. Send me an email to homeworksolutions@mathmeeting.com. And I just want to thank everyone for coming. I can't tell you how much I enjoyed doing this. This was super exciting. I'm planning on doing this as a weekly thing. So stay tuned for my next one. And once again, I want to help you guys out. I want to create lessons based on what you guys want me to do. So just send me an email to LiveStream@mathmeeting.com. Let me write that down for you. For my next live stream, if you want me to work out any problem, send me an email to LiveStream@mathmeeting. Make it a little smaller here for you. LiveStream@mathmeeting.com. Send me an email, and I'm going to create a lesson based on all of the problems that you guys send me. And I'm having a blast doing this. I hope you guys enjoyed it. And I will see you guys in my next live stream. Thanks for coming, guys.